So people going for that concentration are screwed.
I think that has been taken out already.
I was just looking at it online earlier. It's still there.
Still there?
Yep. You should save your password on there.
No, I never save my password on anything.
I'll tell you what, go up to Tools real quick. Go to Option, or no, it's Edit Option, Edit Preferences for you. Go to Security. Click the Use a Master Password button. And set yourself up with a master password there.
No, the whole idea is to enter the password every single time so I don't forget my password. I know what you're saying. You're looking from the technical perspective. I'm looking from the, my mind is going perspective.
No, you're not that old. What are you, like 22, 23?
It's the mileage. It's the mileage. I am. Yes.
I've got a question. In your assignment page,
yes.
You say that it requires 2 parameters. In the file you gave us for the testing, you input 3 parameters, and if you look at your main function, it requires 4 parameters. Can you explain, please?
Okay, absolutely. It is my...
Someone submitted it already?
It is 3. Okay, the answer is it is 3, so let me fix that first. Okay, because there are 3. Well, okay, when you look at ARGC and ARGV, the command itself is the first quote-unquote parameter. And that's why there are 4 items in the array in order to have 3 actual parameters.
That explains the 4.
Yep. And where did I mention 2?
What numbers actually correspond to? The 799?
It should be number 2 in this base.
It's the base of the first number and then the base of... okay, this is the base where it is going to... This is the base of the powers. And then 9 is the base, of what it will print.
So it's printing 7 to the 9th power in base 9.
No, it will find all powers of 7 that are less than or equal to 2 to the power of 32 minus 1. But to print out the powers of 7, huh? Say it again. Well, it's all being recorded, so you guys can watch it again. Not because I'm mean, but because I'm forgetful. There's a slight difference between the two. I cannot remember what I just said. I can try my best.
Can you go back in the video and play it back for us?
Not right now. I mean, it's not a... I don't think we can TiVo it. Maybe we can. Okay, let me see if I can do something like this. It might break the recording, but we'll give it a shot. 2011 0428 310.flv. Oh, I can do that. Cool. And it is. So this is lagging behind. I'm TiVoing myself.
We're watching the in-progress recording of the class as it's going.
From the technical perspective. Okay, so listen now. Okay, absolutely. It is my...
Someone submitted it already?
It is 3. Okay, the answer is it is 3, so let me fix that first. Okay, because there are 3. Well, okay, when you look at ARGC and ARGV, the command itself is the first quote-unquote parameter. And that's why there are 4 items in the array in order to have 3 actual parameters.
That explains the 4.
Yeah. And where did I mention 2?
Numbers actually correspond to 799.
That should be number 2 in this base.
It's the base of the first number and then the base of... okay, this is the base where it is going to... This is the base of the powers. And then 9 is the base, of what it will print.
So it's printing 7 to the 9th power in base 9.
No, it will find all powers of 7 that are less than or equal to 2 to the power of 32 minus 1. But to print out the powers of 7... Huh? Okay. So this is great. We can throw ourselves in a big time loop here.
It's like being in Spaceballs again.
Okay, let me make sure the recording is still going. Okay, so that did not break it.
So you've
Very
got a
good.
recording of the recording.
So yes, we can now do a time loop thing, so it can keep going on forever and ever. Okay, let me just look at the program first. Okay, yeah. Did we take a look at the program last time? No. Oh, because I didn't do it. Okay, that's also that's not a time loop. It's a forward travel in time, right? Okay, so let me just do this part. Yeah, I'll go ahead and download this file.
So what's the answer to this one again?
42.
7. We already did this homework. Now you're going to show us the answer.
Look, it was submitted assignment. It's finished. Someone broke it.
It's easy to make homework assignments like these, because all I have to do is to write the C part, and you guys have to write the assembly part. It's also easy to check whether yours works or not. I just have to compare it to the behavior of the C version. Whether it is right or not doesn't matter, as long as they're consistent. I'm just kidding. Okay, so this is the program. This is the program in C. Print base is print base is already done. This is not the one that you have to write in assembly. So when you look at print base, it's not a big problem. It's the same thing as last time. In other words, print base is you're printing the value of parameter n, but using the base specified by parameter b. Okay, so n specifies the value that you want to print, and b specifies the base that you are using to print that number. Yep.
So what's the second N9 for then?
Because there are if you look at the main program, okay, this is the main program. I did not really use a lot of error checking. I'm assuming people are inputting something that is relatively right. Okay, let me just kind of go through this from the beginning. Did you guys talk about how to pass parameters to the main function in your C++ class? Sort of? No? Okay. I can see some people nodding and some people, shaking their head. Is that because, some people come from not ARC or some people come from ARC or not? Did either Iraj or Damon talk about this in the C++ class, P360? No? Okay. This is a really cool thing, because it allows you to write a program that can take command line parameters, which obviously is a very handy thing to do if you're writing a program that can be run through the command line. When you do that, you have to supply these two parameters. The first one is argc, or the count of arguments. Okay, it tells you how many arguments there are on the command line. It is already parsed. It's not giving you the entire command line. It's giving you components of the command line already parsed. The second one, which is argv, is a pointer to a const char. You can locate it as an array of const char strings. In other words, if you do not like it like this, you can always change the way it looks by making it more like that. It is an array of strings. Okay, it's an array of strings, and the number of items in the array of strings is specified by argc. Is that okay so far? Now, every single program starts with argc at least being 1, because the command to start the program itself is the first argument. If you say /main, 799, /main is the first string. It is argv bracket 0. Is that okay? And that's why we discount that one immediately, because we don't really need to use that one. Yep.
How does that become useful?
How does it become useful?
Yeah, why would you ever need to know?
If you know how your own program is invoked, there are certain things that can be useful. For instance, what is the name of the executable? Because someone can potentially change the name of the executable. Yep, go ahead.
BusyBox. That's
BusyBox.
a single binary with a bunch of symlinks pointing at it that's used in routers and embedded systems.
Right.
Where, depending on which symlink you type in to invoke the program, it's what's called a multi-call binary. It just uses a lookup table to figure out what it's going to do.
Okay. So that there you go. That's a nifty trick.
Yeah.
I never thought about using that.
So you get one program with all your libraries and stuff built in.
Mm-hmm. Cool. Okay, and then we have, so in the program, I have to look for exactly a count of 4 for all the arguments, because we need the command itself and then 3 more numbers for that. The 3 numbers are x, y, and z. They're all initialized to 0. And so that if the program finds out that the number of arguments is not exactly 4, it will print out this error message, and then it will just quit, because only this else will actually do the rest of the program. Everything else will basically just print the message, and then there's nothing to be done. Else if, which means argc is in fact 4, then it will do a string scanf to try to interpret the first number as a number. If it cannot be interpreted as a number, then it will return a non-1 as the return value. Then I know for sure that the first parameter was not a number. I just print an error message and then exit the program. So it will do the same thing with the other two, the y and z. And by the time I get to this one, if this one returns a 1, that means everything is good and I can move on to this part of the program. This part of the program is invoking print base. The first parameter to print base is the return value of powers, and I am printing that using z as the base. In other words, the last power of x is printed in base z, but everything else are printed in base y. So you have an option to change the base of the very last power of x.
So that's what the last 9 is for.
Hmm?
So that's what the 2 9s are for. 1 is for the power.
Correct.
1 is for that print base.
That is correct.
Okay.
Yep. Any questions about this? Nope. Okay. So your assignment is to implement print powers. Is it powers? Let me see. Yep, that's your homework assignment. Your homework assignment is to implement powers. Powers is there's nothing tricky here. There are no pointers. There are no structures. There are no arrays. It's just integers. Stuff that we have already talked about. From last week's perspective, or before the break perspective. But it does call compare, which is a C subroutine here. It also calls print base, which is also a C subroutine here. Okay, but itself, powers as a subroutine is also called by main, which is also a C subroutine. In other words, the subroutine that you are writing in assembly is sandwiched. On one end, it is called by main. On the other end, it has to call compare as well as print base. You can, if you want to, you can also call write. I mean, it works exactly the same way as any other subroutine. But I would just use, interrupt or system surface number 4 and deal with it that way. I mean, it's not any faster or slower either way, not by much anyway. Are there any questions? Yep.
My question was, I guess it's just I'm not sure I do it, but in your test case that you ran, the last number is a 64-bit number.
Is it?
It's 5 billion, which is over, and it runs fine when you run the C program.
Right.
And it runs fine, but I have it working up to that point in assembly, and then it doesn't print that last number as it is. It overflows it and prints it.
That is interesting. Because it's not supposed to do that. Okay, if n times b1 is greater than n, then it gets out of the loop.
I mean, it could be something else.
Could be, but if it's printing a number that cannot be represented in 32 bits, then there's a problem.
Well, how exactly is it printing? Is it printing each number like once, like that? That last number is like 5 billion something. Just
Yeah. Well, let me run that again. Just I'm pretty sure what you said is true. I just want to give it a try first. Oh, I don't have a. Let me decompress it first. So the first thing you guys have to do is to decompress this whole thing into its own folder. So let me do that first. Go back. And I'll extract it to today's folder. Somebody has to remind me to upload both the one from the 26th and also the one from today. Oops. Wrong class. Okay, I know what it is. This is a number in base 9. So it is actually in base 10. It would be less than or equal to 2 to the power of 32 minus 1. So I think it is still okay. I think the program is still working correctly.
So the assembly program should print that number, or
Yes.
So it still will print that number.
Well, the program should still print that number, correct? Yep. Because this number is actually still less than the maximum of a 32-bit number. It looks like it's 5 billion something, but it is printed in. Remember, it's printed in base 9, and not printed in base.
Just do 7, 9, 10. Let's see what it is in base 10.
Well, let's do this.
Still a billion.
Yeah.
So it's a base. The other one was a base 9 number. If I do it in base 10, it is quite a bit less than the 4 billion. It's less than 2 billion actually. So it should work. So you can basically just change the base system. If you use 7, 10, 10, then all of these are powers of 7 printed as base 10 numbers. You can change base 10 to base 8. Then they're all printed in base 8. Okay. But print base is the one that is actually kind of complicated, with all the math stuff and whatnot. But that's done already. Your job is, just powers. Okay. Any questions about this? Now there is one thing that you guys have to be kind of careful about. If you want to store something in a register, call a C subroutine and come back and continue to use the register. The C subroutine can possibly have destroyed that register. So if you want to use a register, it is best to save it before you call a C subroutine and then restore it, after the C subroutine returns, just in case the C subroutine is messing with it. Okay, the only registers that are guaranteed to be preserved are EBP and ESP. So those two you can count on to be exactly the same before you call the subroutine. But everything else, everything from EAX to EDX, ESI, EDI, and so on, you can probably assume that those can possibly be changed. Okay. Any other questions about the homework assignment? Now the homework assignment is kind of, in a certain way it's easy to do because the makefile is already done for you. If you read the instruction, you can say make main C. It is already up to date, so there's nothing to do here. This is the one that is already done. In other words, if you look at main.c, and I can show you that trick in C. So what I do here is I have a conditional compilation here. This is called conditional compilation. This is processed by the C preprocessor. If a macro called CIMP or C implementation is defined, then it will basically leave this part intact and it will be compiled by the C compiler. If this macro is not defined, then this portion will not even be seen by the C compiler. Then it leaves the room to use your own assembly implementation that has the same name. So that's the trick. This is the trick that I use, so I can use the same source file, but it can, by changing the target or changing whether a macro is defined when you compile, it can change whether to use the C implementation or use your assembly implementation. If you look at the makefile, it actually just pretty much explains how everything is done. There are two executable targets. The first one is main, and main is compiled using powers as one of the object files. The other one is main C because it is all done in C, and that one has this one little extra thing here. Dash uppercase D allows you to define a macro on the fly when you run the compiler.
So it is not included in one of the header files nor the C file. It is defined by the command line that runs the compiler. And this is a very nifty trick. Linux, as an operating system, uses this trick left and right. When it comes to modules and other things that need to have, something globally communicated by macros. But you don't have to worry about this stuff here. It is already done. So basically, what you need to do is to go to powers.s and write your subroutine, between the label and the return. And when you're done, you just have to say make. Because make will make the first target. In this case, the first target is the main subroutine, which is the one that will use your assembly implementation of powers in the code. So from your perspective, all you have to do is to say make and then GDB main. Do not GDB main C, because that's always going to be correct. It is using the C version of the code.
It'll make us feel better about ourselves. It's right.
Until you find out, oh, I'm supposed to run main. Okay, so is that okay? Does everybody understand the workflow for this homework assignment? It's a little bit different from the other ones, but I think the make file will would definitely make it easier. Okay. So when you're all done, I also have a target called make tar. So that will just tar up everything and create the tar file in your home folder, and you just have to download that to your PC and then upload it to Moodle, and you're all done. Okay. Are there any questions about this? Is anyone feeling a little bit cumbersome that you have to get this file from the virtual machine back into your Windows environment and then upload it to Moodle? That one extra step? No? Okay. I was about to tell you guys how to avoid that, that one step. If you
I find that to be cumbersome.
If you run, okay, I'm assuming that you don't want to get rid of Windows because you still have games that you want to play. Okay. What you can do is you can use the same thing that I use, which is a live distribution of Linux. And once you have that, you can run the virtual machine just like you run the virtual machine with this homework assignment. Except the one that I have also have a browser. So from inside the virtual machine, you can now go onto the internet. For instance, some profs. Then you can turn in the homework assignment, right away, because from the virtual machine's perspective, it is the same machine. That's the same machine that you actually do the development. Nifty. It is very nifty. And someone may say, but that's going to chew up a lot of memory resources. It's, because you are running a graphical user interface inside an emulated PC that itself is a virtual machine inside another, operating system. It really is not that bad, because if you look at the resources consumed at this point, okay, let me show you the resources that is being used at this point. Where's the monitor? System monitors right here. So right now I have all these things going on, which is what you will need to do your homework assignment. I don't think you will need any more than this. If you look at how much memory is used, it's using 400 megabytes right now. In other words, if you give the virtual machine half a gig of RAM, it'll be fine. It's not going to be screaming fast, but it will be fine. So that means it is entirely feasible to run the graphical user interface of Linux inside the virtual machine if you want to do it that way. Nobody wants to do it.
Let's stick with where we're going.
Yep.
How can we upload the sum cost from the command line?
That's a lot harder because you have to authenticate as yourself first. It's not impossible. You can do it, but you have to, as far as I'm concerned, the best way to do it or the easiest way to do it is to use Perl. Because in Perl, you can use, there's a particular module where you can download, you can turn your Perl program into an HTTP client that is capable of authentication, maintaining sessions, and stuff like that. So you could do it that way if you wanted to.
Or you can install Linux.
But it's possible. You can do it. It's just, you also have to know the link, to the upload interface, which means, you will have to capture that URL, somewhere else first. So I'm not sure how much time you can save by writing that script. Okay. Any other questions? Any other questions?
Do some of the samples?
Hmm?
Can you do some of the samples?
examples, but we have done it already. What?
On the files you haven't uploaded yet.
Yep, well, that means I just have to upload the files, right? I can always do that. I mean, I can always upload the files.
Can you upload that submit assignment too?
Okay, I'm going to upload, the one on the 26th.
Because we have less time compared with the previous assignments that we have until like next Thursday, but this assignment just on Tuesday, so we have less time to do it. So just give us.
No, you have 1 week. You have exactly 1 week, just like with all the homework assignments.
It's Tuesday.
Yes, but it was assigned on Tuesday too.
Okay. Yeah, but you didn't go. But you did not explain it.
Now, I'm going to check who actually, checked the homework assignment on Tuesday. Who clicked it on Tuesday. Let's not go there, okay? All right, 2011 0428 26. 6 2 6.
Better protect it 2.9. Wow, from the future.
Future, yes. Well, I'm pretty sure 2.9 already in some countries like Japan and China is already 2.9.
Okay, then 30. Fine, whatever. Why not just do January 1st, 2013, whatever it is? Just be done with everything.
Okay, where is it? 2.6.
It's rolling.
All right, so now we have the files from Tuesday uploaded. Okay. But this is stuff, but this homework assignment really does not use anything that we talked about on Tuesday. It only uses stuff that we talked about before the break. Like 2 weeks ago, exactly. So maybe I should make today the due date. Yeah, just to make sure that people show up in the lab. It's really quiet. It's really way too quiet in the lab.
Remote activity.
Okay, so so that is that. Okay, the homework assignment is already done, and we have covered all the material already related with this homework assignment, which is basically how do we pass parameters and how do we utilize parameters inside the program. And we talked about all of that stuff already from before the break. We continue to use many of those things that we talked about, even though we are now talking about structures. So it's just a matter of associating the sample programs that we do in the class with the homework assignment. That is basically what you guys have to do. Now I did change my notes. You can see the date here. This is April 28th, 2011, because I just updated that. In fact, if you read, okay, let me just go back a little bit here. Okay. And okay, I just sent you guys an email because I found a problem. Remember on Tuesday I could not get the program to work, and that's because I did not have a good understanding of the C standard. As it turns out, the callee is responsible to free the pointer to the return value area. I did not know that. Okay, and that's why it did not work. So that's why I sent an email to all of you, and also include a link to the page that got updated as a result of that. So this is the page that got updated, and I'll just go ahead and highlight the portion that was updated. Okay, it's starting from here. It is important to note that GCC, and I'm assuming that most other compilers will do the same thing, it assumes the callee to deallocate the pointer to the area reserved for the return value. Now, because of this, okay, if you read this sentence here, which is a really long run-on sentence, this only applies when you're returning a non-scalar value. If you're returning an integer, it does not apply. If you're returning a pointer, it does not apply. It only applies when you're returning a structure. And that's why it only applies to this slide, because only this slide talks about returning a structure. So normally this is a little hard to do, although not impossible. So basically we can do the same thing by these 3 instructions. To replace the single return RET instruction, you have to replace it with these 3 instructions when you are returning a structure. So let's take a look at these 3 instructions and find out what they do as a whole. We already know that the first and the last instruction, pop out and jump, they are basically just the same as return, because what we are doing is with a pop instruction, we are retrieving the return address in this case and put it into the register EAX. Let me bump up the font size. Okay. So this instruction is just going to retrieve the return address and put it into EAX. And it doesn't do anything with it once it is in EAX. The last instruction, jump asterisk EAX, is going to continue execution using the address stored in EAX. So these 2 instructions, pop out and jump, they combine and they just do what we normally call return. But there's one instruction sandwich in between, which is add for ESP. When we are adding a positive number to the stack pointer, are we allocating or are we deallocating?
Deallocating.
We're deallocating. And what exactly is it deallocating here? The pop L is deallocating the return address already. What is directly on top of the return address?
The area we allocated for
the pointer to that area. Okay, the pointer to the area that we reserved when we return the structure. Okay, so that means this sequence of code, these 3 instructions, will automatically deallocate that pointer, which is expected from the callee when you're using GCC. And this is I did not expect this. Okay, I did not know about this on Tuesday, and that's why when I use my program, I did not make the assumption that those 4 bytes were already free, and that's why the stack was off, and that's why the mem copy did not copy correctly.
I like that return statement though.
This return statement does exactly the same thing. RET $4 is basically saying I will do the same thing as a return, but at the same time I will also free 4 bytes, because of the $4 in this case. So you can actually say, return $20 if you want to free 20 bytes after the return address is popped. Okay, it's kind of handy, but I think it is kind of dirty as well, because you're messing with the stack, and I personally do not know why it is up to the callee to remove those 4 bytes, but since it is already done.
What if they want that pointer back?
Why would you want that pointer back?
Doesn't matter. What if the caller wanted the thing back? The function shouldn't have any control of anything not allocated by the function itself.
Well, that pointer was set up by the calling subroutine, but by the calling code to begin with. So the calling code already knows where the reserved area is. The whole purpose of that pointer is really for the subroutine, the callee, to find out where the area is. But the same argument applies to all the parameters as well. So it just doesn't seem to make a whole lot of sense to me, but that's basically what the standard says. Yep.
So what happens if once it's been deallocated, someone pushes something on the stack?
Sorry?
What happens if once the callee pops it off the stack, something pushes something on the stack before the caller can retrieve it?
Then it's gone. But these 4 bytes is only the pointer to the area reserved for the return value. It is not the area of the return value itself. So your return value is perfectly safe. It's still there. Okay, if you just continue to read this part, what I did is I changed this from $12 to $8. Because when I used $12, I was assuming that the calling code is responsible to free all 3 things on the stack. But as it turns out, one of those items is freed by the callee already. So as a caller, I only have to free 2 things instead of 3.
It's good to know in any case.
Well, it's good to know for your next homework assignment. I guarantee that.
Oh.
Yep.
Safe stress.
Yep.
Where did you go to figure this out?
How?
No, where?
What?
Where? Well, I got a suspicion, on Tuesday, because remember on Tuesday, when I was debugging that, I was looking at, I was taking snapshots of ESP, the stack pointer before and after the call, and before the call, it was clearly 4 bytes lower than after the call, but it's not supposed to change, between, the point of time that you call and the point, after it returns. So I was suspecting that the caller was doing something, but I was suspecting the debugger was doing something funky with the stack pointer. But then I thought about it and say, but the debugger was in assembly debugging mode, and it should not be messing with the registers as a result. So I was just suspecting that. Then I looked into the disassembled code of the subroutine, and I found out exactly what it does, and that's one of the things that it does is it had this instruction at the end. And then I look up, what does it mean when you specify a number after RET, and that's exactly what it was. So it took a little bit of detective work, maybe 10 minutes or so. Once I found out that the stack pointer is in fact offset, then it's just looking that up. Yep.
How did you disassemble the program?
OBJ dump can do it. There are a number of ways to do it. The OBJ dump is one of those. Yeah, those are dark secrets of of developers, because you can use those techniques to reverse engineer programs as well. Because once you can disassemble an executable, you can look into the executable and find out how things are done. And there are programs called decompilers. Has anyone heard of the term decompiler? Yeah. Okay, and what do you think a decompiler does?
Takes the object code and puts it into the source code.
Yep. Or try its best to put it into source code, because a lot of times you cannot have meaningful variable names anymore. So the code is a little bit harder to read, but nonetheless it will try to put low-level code like machine code back into a semi-high-level code where there are comparisons, loops, and conditional statements. Okay. So anyway, are there any questions about returning structures? Because that's what we talked about on Tuesday, and the sample program did not work because I did not know about this part. No questions? Okay. If there are no questions, we'll move on from this note. And the next one, which is the only thing that is remaining, is how do we deal with arrays? Well, what do you think? How do we deal with arrays? Well, first of all, let's think about what does this mean in C? Uppercase T, ARR, as the name of the variable, and then square bracket 100.
You're declaring 100 objects of type T?
Exactly, okay? That's exactly what I'm doing. The size of this array is going to be, this is all in C code, basically size of is an operator that you can use on top of a structure, an object, a variable, a pointer, and so on. And it tells you, the size in number of bytes that is taken by one single type T object. And you just have to multiply that by 100 because the array has exactly 100 of those elements. And then the calculation of the address or the base address of element I is the same as this. In C, you can do it like this, pretty easy, okay? Because, this is the element itself. This is the address of the element itself, and this is the address that is casted to a byte pointer, a char pointer. But you can also do the same thing here, which is the longhand of doing exactly the same thing. So what we do is we take ARR, which is an array, we cast the array into a char pointer. So now everything is counted in number of bytes. Then you just add I, which is the index in the square brackets, multiply that by the size of a type T, and when you have the whole thing here, it is still a char pointer, but these two should be exactly the same. Is everybody convinced that the left-hand side and the right-hand side should be exactly the same, and this equality should always return true? Sort of? Kind of? Okay. There are no questions about whether we should do multiplication first or addition first? Good.
What about the division?
In cisp310, I have constantly have people asking, should we do the addition first or should we do the multiplication first? Do they talk about this in like high school or elementary school stuff?
Elementary school. My third grade teacher did it.
Third grade, okay.
Been doing
So-
this since kindergarten.
So it is not unreasonable for me to assume that people understand multiplication comes first when even with the lack of parentheses. Okay, very
You
good.
should still always use your parentheses.
Or use postfix notation, where parentheses are not needed.
Or
That will be your
3F.
next homework assignment. Postfix parsing.
No.
Fine, that'd be fun.
That'll be fun.
But you should use reverse Polish notation instead.
Yeah. Okay, we'll use RPN. That's fine. That would be cool. Well, we already have already have subroutines to parse numbers as an input, right? And now we understand arrays, so we're good to go.
Yep, now all we need is reverse Polish notation. Have us write a calculator.
Okay, now there's no more notes here. Okay, there are no more notes to say, how do we deal with, array indexing in assembly? Why do you think I did not say anything after this in terms of accessing an element in an array?
Because we've already got base scaled indexed mode.
That will only work if your element size is 2, 1, 2, 4, or 8.
Yeah, but it works.
It does not work on anything else. But if you look at this expression here, is there anything here that we have not talked about how to implement in assembly? Casting. Casting is not needed because everything has no type in assembly. Very good, good question. Did we talk about the multiplication? We have the mul instruction. This is a regular addition. And whatever comes out, is a pointer. But in assembly programming, there's really no such thing as a type. Okay, all it is just a number. Whether you use it as a number for calculation or whether you use that number to dereference into a memory location is entirely up to the instructions that you pick and also the operand that you pick. Okay, there's no such thing as a pointer in assembly language programming. Are we doing okay so far?
Mm-hmm.
What about this part here? How do we know the size of a structure of something like this? We talked about that too.
Yep, we
Yep.
wrote a C program to do it for us.
Exactly. You write the C program so that you can know exactly how a structure is implemented. Okay. So you can look forward to this, all this stuff here being used in your next homework assignment.
Yay.
Well, I'll give you like a basis to start with. I mean, you're not going to start from scratch. You still have to do something, to show that you understand all these concepts.
Are you going to give us the C program that will print out all the labels for us? And we have to
I'm still thinking about RPN parsing. Well, let me just kind of go through RPN parsing so that you guys, have some understanding of what it is about first. Okay. RPN parsing, it sounds really bad. It sounds really hard, but it really is not. It is one of the reasons why it is used in older HP calculators.
Whoa. The newer ones use it too.
The newer ones too?
Yeah.
Excellent. I actually have a calculator app on my Android phone that has RPN because I cannot deal with infix notation. I can only deal with postfix notation. Yes. Okay, so let's go through this part here. It is going to be helpful also to people who want to deal with compilers later on, okay? Because parsing is parsing. Okay, so let me just show you something like this. Okay, what is and just to make the whole thing a little bit more complicated, like this. Okay, do we know what needs to be done with this expression? Okay, and this is called
It's a decimal value. No, it's not. Never mind. Sorry.
okay. This is an infix notation, right? It's called an infix notation because the operator is standing between the two operands. Okay, what do I mean by two operands? Okay, let's start with the addition, which is the first thing we have to do. The addition operator is sitting between 6 and 7. 6 is one operand, 7 is the other operand. The multiplication is sitting between 5, which is one operand, and this junk here, which is the other operand. The division is standing between, this entire one side is one operand, and then 2 is the other operand. So the operator is in between, and therefore it is called the infix notation. We were taught from elementary school to use infix notation. In hindsight, that's a big mistake. Just like
so infix notation is wrong. The decimal system is wrong.
yes, that's my
Reform education for it.
That is my political platform. If I'm going to run for anything, that's my political platform.
Let's make everyone computer programmers.
I will start with reforming, infix notation, change it to postfix notation, change, base 10 to base 2.
Good luck with that.
There are 10 types of people who understand binary.
Well, I'm still hoping the board will fly by and pick me up, so, that's my hope.
They don't use binary, they use trinary.
Hmm?
They use trinary.
Trinary. Yeah, well, but in postfix notation, you can do that as well. Okay, so that's one. Okay, what about prefix notation? What do you think prefix notation looks like, to express the same calculation?
2 divide, parenthesis.
Okay, so we divide something by 2, and that something has a multiplication in it.
Yeah, 5, and then that's another parenthesis.
And then we have plus 6, 7. Exactly, this is called the prefix notation.
That makes no sense.
Okay? Well, but you should know this already. We know prefix notation not by the name prefix notation. We call that subroutine call. Okay? If you have, any type of subroutine called like divide or multiply and add, this is the same as calling divide. And in divide, you have the first one is multiply, and then inside multiply, you have add. Okay, well, excuse me, we have a 5, and then you have add 6, 7, and then you have 2 on the outside. Can we do that with subroutine calls?
Absolutely.
Yep, so subroutine call is automatically a prefix notation because the name of the subroutine precedes the list of parameters. Okay, so prefix is nothing new to us. It's just that we have never seen prefix notation using just parentheses and the name of the operators. This is the way things are done in Lisp. There's a programming language called Lisp, which stands for list processing. It used to be a really popular programming language for AI applications, artificial intelligence applications. Okay, so all of these is done. What about, I don't like, prefix notation either. Guess why? I don't like parentheses. Okay, it's already kind of bad with like 3 levels of parentheses. Now with VI, it really helps because VI has the ability to match parentheses, square brackets, and as well as curly braces. So when you close something, it will highlight the beginning of that. When you put a cursor to the beginning, it will highlight the end. So you always know, where's the other side of the, parentheses, square brackets, or curly braces. Okay, so having a good editor really helps in the case of parentheses. But parsing this is actually also a little bit difficult in terms of programming. So let's take a look at the postfix notation. The postfix notation of this, there are several ways to express the postfix notation. One way is to express it like this: 6, 7 plus 5 multiply 2 divide. Okay. So let's figure out what this means. When you say 6, 7, okay, when you say 6, you do not specify what you're doing with 6, so it will just, remember 6. When you say, it is push it on the stack. When you say 7, it will say, well, you don't say, you're not saying what to do with 7, so it will put 7 on top of 6 on the stack. When you specify plus, then it will say, oh, okay, I'm supposed to add something and produce a result. But add will require 2 things. Let me go to the stack and pick up the last 2 items, on the stack. Turns out to be 6 and 7, right? It will perform the addition, and the result of 13 will come up. Well, but what do I do with 13? I don't know. Let's put it back onto the stack. Okay? So now you have 13 on the stack. Then it will encounter the 5. What do we do with 5? I don't know. Put it on the stack. Right? So now we have 13 and 5 on the stack. Then we see the multiplication. Okay, the multiplication is an operator. An operator will say, okay, I will need so many items from the stack. Some will only require 1, some will require 2, some possibly can require 3. But in this case, it only requires 2 to do the multiplication. So it will pick up the 2 items on the stack, on the top of the stack. So it will pick up, in this case, 13 and 5, and perform the multiplication. 13 times 5 is 65. So the 65 will be put back onto the stack. Then it will encounter the 2, and it doesn't know what to do with 2, put it on the stack. So now we have 65 and 2 on the stack. And then it will encounter the division, which says, oh, pop the last 2 items on the stack. The deepest one, or the older one, becomes the dividend, and the younger one, the more recently pushed one, will become the divisor. Perform the division, and then the result, which in this case is 65 divided by 2, which is 32.5, will be pushed back onto the stack. Yep.
Why don't we add a couple of numbers to the beginning of this and a couple of operators to the end and see what happens?
What?
Just like go to the very beginning of the line and type like 3 space 5 space 22. And then go to the end of the line and put like plus and divide.
We don't want to put tag through that.
Yep, go ahead.
The real trick to this is that it ignores order of operation. It just goes left to right.
Exactly. There's no implied order of operation. There's no such thing as operator priority. Because you just do the operation as you encounter the operators.
So then it's up to the person writing it to understand what they want to do.
Exactly. Exactly. But it doesn't use parentheses either. So there's no nesting of parentheses, because the so-called nesting is now done by the stack. It is not done by parentheses anymore. Okay? The question is, are there any programming languages out there that will utilize this kind of obscure notation?
Don't they all, they just translate our index notation into postfix?
Exactly. When you input something like this in a program, like this is all translated by GCC into a postfix notation. Then it will go through an intermediate form of code, and then it will emit the actual code to perform the calculation. Okay? Has anyone heard of it's not a programming language per se, but it is actually a programming language. It's a scripting language. It's called Postscript. Has anyone heard of Postscript? Only 1 or 2 people?
Is that something on our English assignments?
No, Postscript is, in short, PS, is an Adobe product. Okay?
Oh, yeah.
It's an Adobe product, and the idea is you tell the printer what kind of shapes, what kind of font you want to print, and not exactly which pixel should be black and which pixel should not be black. Okay, so it's not a raster type of specification. It is more like a vector, graphics specification. And the name Postscript comes from the fact that it uses postfix notation when it specifies these operations. So when you want to draw a circle on a piece of paper, on whatever medium you want to use, you specify the center, you specify the radius, and then you say draw circle. Okay, because it's using the postfix notation. There is a relative of Postscript that we use almost on a daily basis. Can someone name that relative?
PDF.
PDF, exactly. Portable document format is a descendant of Postscript, and it shares a lot of the same encoding technique that they use in Postscript. So this is nothing new. I mean, people have been using this, for a long, long time. Old HP calculators and new ones, continue to use it, even though the new calculators can deal with parentheses too.
Yeah, they actually come programmed to algebraic mode. You have to turn RPN on.
That's just wrong.
That's because people buy an HP and don't realize how to use it, so then they return it if it's an RPN.
Maybe they should have a big, panic button. When you pound on the panic button, depending on how hard it is pounded, it will switch. Okay, I'll switch back to Infix Notation.
Shouldn't be a don't panic button.
So that's postfix notation. So the question now is, if I want to write a program to parse postfix notation, how would you do that?
Push function call, push function call, push function call.
You will need a push and a pop, right? Okay. Now, since we already we cannot use the stack of your program. The program stack itself cannot be used because we use it for many other purposes. So that means you have to use your own array to store the numbers to be processed. What?
We can use the system stack as long as we do all the processing of reading the next item in the same subroutine. Then as long as we push, call our operator, store the return value, push it back on the stack, we're done. We move on to the next.
Go ahead. I don't think it can be done easily.
Well, since add would be a subroutine itself, it would be push, call a subroutine.
But it doesn't.
But then you're getting rid of your return address. You can't.
Exactly. Something is in the way, so you cannot just use the system stack for this purpose.
It uses EAX for your return address.
You have to do certain tricks to do it. It is better not to use the system stack. It's just a whole lot easier if you use your own stack to do it. How many people know how to implement your own stack using an array and either a pointer or an index? Only one or two? It's okay. I will give you the source code in C, so it's not going to be. All you have to do is to follow the code. Okay, it's just stuff that we should be able to do. Yep.
Are we going to allocate our stack on the stack or the heap?
Yeah, why not? I mean, it doesn't make any difference whether your calculation stack is actually a part of the system stack. That should be immaterial. Okay, so kind of look forward to this as your next homework assignment.
You should make writing it from scratch our next homework or our next final.
To make it utilize actual structures, let's turn these numbers into complex numbers. So we have a reverse Polish notation thing that will work on complex numbers.
Better give us 2 weeks to do it.
Let's give us fractions instead and require us to reduce them.
No.
I'll think about something. But your
form.
next homework assignment will definitely require the use of structures and possibly arrays at the same time. Let's take a look. I mean, it sounds complicated, but it really is not. It really is not as complicated as it sounds. We are basically done with all the notes already, so it's time to just look at the sample code.
Stack.
What?
We should use a dynamically allocated stack, where each item on the stack consists of the value that we've just pushed on the stack and the pointer to the previous item on the stack.
Okay, so what I'll do is I'm going to give you guys, some sample code. So I'll give you some really obscure definitions, and then, you will have to tell me, how to get to it, assuming that we have symbols, defined already, for the structures and the size of the structures and so on. Okay. So here is the C code, struct X. See that? That's the magic of VI. When you put the cursor on one, it will highlight the other one.
I couldn't imagine programming without syntax highlighting.
This is not even syntax highlighting, it's just parentheses matching.
Oh yeah, that's what I meant. Or syntax highlighting for that matter.
Okay, so we have int I, and then we have, say, int j. Okay. So now we have an array of struct X. So let's just deal with this one here, and let's just say that we have a stub subroutine, and inside
what you did there.
Huh?
A stub subroutine.
A stub subroutine. Oh.
No, you're right.
I'm just putting the definition inside the stub subroutine, and my question is, how do we do? Oh, let's see. Let's do with something that is relatively easy first, and then we'll move from there. Okay, so we have int I, and then we have r bracket I dot j gets. Let's just say we initialize that to 0. Okay. Okay. Just to be sure, so no one criticizes this code, something to initialize I. Okay. Something to figure out what I is supposed to be.
Did you say int I equals 0?
But then if you note, I is always 0, in this case, that makes the code easy. Okay, so the question is, how do we implement this line of code here? Okay? And just to make this a little bit more, interesting, let's say we have dot 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 here. something else. In other words, it's not exactly 8 bytes. We don't even know exactly how many bytes it is, except it is defined by the symbol x underscore size. Okay, x underscore size will define exactly how many bytes we need for one struct x. Yep.
Can you put in those symbol names in there as well?
Hmm?
The x underscore size, the x underscore I size, the x underscore
We assume
A
those are
size.
already defined.
Can you just put them in there to make it easy?
What about ri.I? We're not going to initialize that?
Okay, let's say x underscores I is already defined. Well, we are assuming those terms are already defined. So we assume, okay, how about this?
But having the names
Assume-
there makes it easier.
Okay?
No, what about, in your little stub function, you have ri.j is 0, but you don't have ri.I. You're leaving one member of the structure undefined.
Yeah,
Okay.
but I only want to implement that one single line at this point.
Okay.
Okay? Assume that R is also defined. In other words, R as a symbol ARR is the displacement from where EBP points to the beginning of the local variable array. Is that okay? Which is our convention, up to this point. And that means, I also need to specify I. So I and R are also defined. Is that okay?
Yes.
Okay. So with all of these, symbols, predefined, our focus is just, how do we do this one single line? What do you think? Well, first of all, how do we get to the beginning of the element that we are dealing with? Okay, to compute the offset from the beginning of R to R bracket I, we can do the following. What do you think the following will consist of?
Subtract the address of
There's
RI.
there's no subtraction.
Multiply x
There's
size
multiplication.
and I.
Okay, so we need to move L, I, EBP to one register. Okay, let's say EAX, right?
No.
Yes.
No.
Yeah.
No.
Yeah.
Just I.
Hmm?
Just I. We're going to multiply the address if you do that.
What? This is correct.
It- multiply the address of for whatever EBP is. No.
Yeah.
Mul or move L I EAX mul X size EBX add L EBP EAX. Otherwise, you're multiplying I plus the
I
address
is
of EBP.
I is a local variable.
Yes.
As a local variable that has the integer that I want, this is the way I get to the integer itself.
Okay.
I don't care about the address of I.
To get to the address, you would move EBP into it and then add I to it. That's how
Yeah,
you
but
get the address.
I don't want to do that.
I
because
know.
Right.
But if right now, if EBP is say 1,000,000 items off the stack and I is 3, you're going to be multiplying 1,000,003 times X size.
No.
No, he's getting
This is a base addressing mode.
It dereferences the address, puts I to it.
It's
grabs
base
that value.
addressing mode, so the effective address is I, which is a symbol, plus the content, plus the value of EBP. That's the effective address. But since it is a base addressing mode, we are going to that location, we're going to the effective address to grab 4 bytes in this case because it's a move long, and copy those 4 bytes to EAX, which is the value of local variable I.
Okay.
Okay.
Your style is just so not what I'm used to.
Yeah. Okay. Now EAX, is the number of bytes from the beginning of ARR, the beginning of the entire array, to the beginning of the element that we want. So how do we get to the address of the element itself? It's it's a few instructions. Two more instructions.
Address of the element.
Yeah.
You put EBP or push EBP on the stack and then add.
We add
Yeah,
EBP to EAX, and there's one more thing to add. The displacement from where EBP points to the beginning of the entire array, you also have to add that to EAX. Are we doing okay so far? No? You kind of have to draw a map in your mind, and then you have to do the calculations. Let me finish this first, and then we'll go ahead and actually use a spreadsheet to kind of document where we are talking about in the address space. Okay, now EAX is the address of the element we want to access. Okay, now that we have the base of the struct X that we want to access, how do we get to member J of that particular structure?
We add the size of I.
We don't need an L anymore. We can actually finish the entire assignment operation. We can just say move L $0 because the right-hand side is just a 0. The left-hand side, which is what we want to store into, is going to be X underscore J, which is the displacement from the beginning of the structure to member J. But since EAX is already the beginning of the entire structure, that will get us to that member. Okay. Done. Okay, so let's go ahead and take a look at the memory map itself and see how all this translates to in what I'm going to do is to kind of use a dry board marker. Well, let me see. Yeah, I think I'll use a dry board marker to do this. It's just a whole lot easier this way. And it also encourages people to kind of come to the class. It's not because I'm mean and I want to, punish people who are not in the class. It's just a whole lot easier to do this, on the whiteboard. Okay, so, and when I draw something on the whiteboard, I always have to specify which way is a higher address because that is very important to establish. Okay, so now we have. This is not right. This is kind of faint. That's still kind of faint. Okay, that's okay. Okay, EBP points to a particular point, okay? And we already know the item, at EBP and also the item on top of that. This is basically what we call old EBP, or the previous value of EBP before this subroutine changes it, okay? And right on top of that should be the return address. And on top of the return address would be our parameters, which we have none in this case. Below old EBP are our local variables. In other words, if I have some other local variables, R may be quite a bit below where EBP points to, but this is our R. Okay, this is our array R. R. And then we have I either somewhere here or somewhere here. It does not matter how I relates to R in terms of memory space. As an array, R, in this case, it is an array of 5 items. Okay, so it has 5 distinct items here. The first one is ARR bracket 0, and the last one is ARR bracket 4. Is that doing okay so far? Does that make sense? Does it make sense that all elements of an array, at least in C, are contiguous? You cannot separate an array into several portions and have the elements not being contiguous. They have to be contiguous. Okay, is that working out so far? Now, when I say this is variable R, I have to be careful and refer to this as variable R because we also have a symbol R defined somewhere. What is the symbol R defining? The symbol R defined being defined is measuring this distance here. This is our symbol R. It's a negative number because the beginning of the local variable R is below where EBP points to. Is that working out so far? Okay. the first part of the calculation, which is the three instructions, the last one being the mole instruction, what are we calculating? We are basically calculating, depending on what I is, we are trying to calculate the distance from the beginning of the entire array to the element that we want to use. So we are measuring this distance here in number of bytes. How do we do the calculation? Well, first of all, we need I, because I is one side of the multiplication. What is the other one, the other number that we need for this multiplication? The size of each element. So assuming I is 2, then we have to calculate 2 times the size of struct X. Is that making any sense? Well, but these three instructions will do exactly that, because the first instruction will move the value of I into EAX. The second one will move the size of each struct X into EBX. The third one will do the calculation. It will destroy EDX at the same time, but assuming the product can be stored in 32 bits, this is perfectly fine, and just say we'll use EAX, we'll just ignore EDX. Is that working okay so far? Yep.
What was that smaller error that you drew? That's where you were looking for the beginning of some element.
You mean this one here?
Yeah.
Yeah, that's okay. Let me. It's fading. It's fading. Okay. So this is EAX. This is EAX after line 22. Line 22. Is that okay? Is everybody convinced that EAX after line 22 is just measuring this distance? The arrow is significant because I need to indicate where is the start and where is the end, because if I don't specify that, the positive and negative can be screwed up.
Little off topic, but if you do a mole and EDX is not used, is it unchanged or 0?
It is 0.
Okay.
It is always going to store the most significant 32 bits
No matter
of the
what.
64-bit product. Yes.
Okay.
So you have to be careful because it is not specified anywhere, but it is destroyed.
Okay.
Well, I should say it is modified, not destroyed, because you may actually want to use it. So it's not always destroyed, but it is always modified. Right? Okay. So are we doing okay up to line 22? Yes? Kind of? Okay. After line 22, we have 2 lines of comment. So by the time we get to line 25, what is EAX after line 25? We are basically adding BP, which is pointing here, to this amount here. Well, maybe I should reverse the 2 instructions because that makes a little more sense. Okay, let's just reverse it. Since it's addition, I can change the order without actually changing the result. Because addition is what? Come on, algebra. Algebra. No. Commutative. You can change the order without changing the result. Commutative, yes. Okay, so once we change the instructions, okay, line 25, after line 25, what is EAX? Before line 25, EAX is just specifying this distance. What if I add
symbol R? Symbol R.
Well,
Yes.
symbol R.
Bring it down.
Okay, symbol R is pointing down here. So if you just add, okay, how many people have taken physics or linear algebra? Okay, you're adding 2 vectors basically. The first vector goes here. The second vector bounces back. So the summation of the 2 is going to be this part here, right? So this will be EAX after line 25. Are we doing okay so far still? Yep, okay. Okay, so now we know that we are specifying this point, but we are not really specifying this point in memory because we are just measuring this distance from here to here. In other words, at this point, EAX is some negative number. It is indicating the number of bytes from where EBP points to to the beginning of the element that we want to access. It is not the address of the element that we want to access. It is how far is it away from where EBP points to. Then we go to line 26. Line 26 is adding EBP to EAX. Okay? EBP is pointing here. EAX is specifying a negative number to go from there to here. So what do you think EAX is going to do after line 26?
It's the address of the element we want to access.
Exactly. So now I've changed the representation because EAX is finally an actual pointer. Before this point, EAX was not a pointer. It is just a displacement from somewhere. But at this point, it is a pointer now. Are we doing okay so far with this? Yep.
So when we use structures in C, the C program has to go through all of this work
Yes.
every time?
Yes. Now that is okay. I will talk about optimization techniques later, because if I is only incrementing or decrementing, you can just add the displacement from where it used to point to. But that's a compiler trick. That's up to the compiler to decide. A lot of times the compiler is smart enough to do optimizations like that. Okay. So are we doing okay? Up to line 26. Are we convinced that after line 26? EAX points to the beginning of the element that we want to access. Okay. Now inside the element we have different members. In other words, this is the element that we want to access, but it has subcomponents. It has member I, it has member J, and then it has some additional members. Okay. Yep. So if you look at a struct X here, okay, so let's say this is a variable or an object of struct X type. It has different components. How do I get to the component J? How do I get to member J? This distance here is which symbol?
XJ.
X underscore J. Okay? The symbol X underscore J specifies the number of bytes from the beginning of a structure to the member J of that structure. Okay? And that's why, on line 28, in one single instruction, we can finish the entire operation. Because EAX is already pointing at the beginning of the entire structure. X underscore J specifies the displacement to get to member J. So when you use the base operand X underscore J open paren EAX close paren, it is already specifying the address. It's already specifying the location of member J. And all that is remaining to do is to move a 0 into there, and I finish the assignment statement. But the thing is, you have to do it one thing at a time. Just like when you read the C code, you have to read it, one thing at a time. You don't look at this whole thing and go like, "Whoa, this is way too complicated. We cannot do it." Because what you do is you do it one step at a time. So let's go back to the C code, and I'll just kind of explain how we do that. The first thing we did was not even R. The first thing we did was to deal with the indexing to get to the displacement from the beginning of the entire array to the element that we want to access. Then we deal with this part here. We find the address of the element that we want to access. After that, once we know the address of a structure, then it is just a structure. It can be just a variable. It can be an element of an array. At that point, I have the address of a structure. Once you have the address of a structure and you want to access a particular member of that structure, which is the last part here, the .j part, all you have to do is to do something like this. The base addressing mode is very handy for that purpose once you have the address of the structure.
And properly defined labels.
Hmm?
And properly defined labels.
And properly defined labels, yes. So are we doing okay with this? I mean, it takes some, mapping in your mind to the actual, layout of memory, and also following the steps, to do it. But that's basically what we do. We just do it one step at a time. Any other questions? Yep.
Not related to class, but
Mhm.
I just heard that anyone who's parked in the Davies staff lot without a permit is probably getting ticketed right now.
Oh,
And I know some people in this class park there.
Where?
Davies staff lot right there.
I parked there.
do you have a permit?
Yeah, I have to stop parking.
If you have staff parking, you're fine. I mean, they're just looking for people without a staff permit and a disabled plaque.
Yeah.
They're doing it now, at
Yeah.
this time.
Like
Wow.
4 minutes ago, I got a text message saying they were ticketing there.
All right, that's interesting. They normally don't do that in the evening. They do it in the during the day.
Yeah, when I got here, there were 3 trucks out there doing stuff.
Probably people leaving their cars.
Yeah, the car in front of me was getting a ticket. I put up my thing in the window. I bet
That's
it was there.
interesting. Okay, so are there any questions about this? Yes? No? No questions? If you guys had to do something like this, would you be able to do it? I mean, not yet.
Yeah. As long as the labels are properly defined, yes.
But I just gave you like 35% of the solution of the homework assignment of next week, right here.
As long as the labels are properly defined, I can handle it.
Well, but okay, wait. Hold. There's one more thing. Okay, let's just take a look at this one here. Okay. I just did this, in the first 5 instructions or so in the original code. The only part that is not here is accessing a member once we get to the element. This will get the address of the element itself. Let's just finish this last part. I just want to make sure that you guys can relate the class node to the sample program that I just wrote. This thing here, okay, if you just look at this part here, is implementing line 20 all the way up to line 26. That's basically what it is. Okay, the highlighted portion here from line 20 to line 26 implements this expression here. Now, it is a little bit misleading because this is really, I'm using the address of the array R, but when you take the address of an array, it is the same thing as just referring to the array itself when you do it in C.
I don't see where you did the typecasting.
Well, my hand is not long enough to slap you, so we'll just pretend. Maybe next time I'll try a higher powered green laser or something like that.
And what you do is you just have to run across the grids and the ceiling here. And just
I know, we'll use, quantum physics.
oh, you slapped him in every other dimension except this one.
No, it's called, what is that called? Entanglement, that's it. Yep. So once we get entanglement down, then I can slap anyone, anywhere. Yep. Instantaneously.
Assuming you can get them to vibrate at the same place.
Yeah, minor details. Yep. Okay. So are we doing okay so far with accessing arrays? Yes. Okay.
It takes time.
It takes time, but you can always try this out. Just make sure that you know what to do. Start with array of integers. Okay, start with array of integers. Yeah, start with something
You can do
simple.
that with base scaled index.
But the whole idea is not to use base scale index, so you can go through all this trouble. If you can go through all this trouble, then you can work with any array of any size of
Then
elements.
why did you teach us base scaled indexed?
Because it is one of the
Because it keeps showing up on the exams?